Welcome to the Cosmic Pie Podcast, Episode 9, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks on a beautiful late winter day.
I don't know about beautiful. I was just walking out in it. It's pretty cloudy and gloomy out there.
I was waiting for you to complain about the low temperature.
Oh, shoot, no. It's not that low.
Last week we had really nice weather.
Right.
This
And
week, a little different.
a little lower.
But I understand things are trending in the positive direction by the end of this week.
That's it.
So we'll wait and see. Now, we do have a live chat feature that's running, so if you have any comments or questions that you'd like to ask us throughout our podcast, please feel free to use that function.
Indeed.
And disclaimer, Robert, do you want to set the tone on that one?
I will keep it simple. The opinions expressed in this podcast are those of myself and Wayne. No organization or other entity is behind us, so it's just us. Blame us.
No government deep state at work here.
No.
Just our deep minds and intellectual prowess.
Okay. Something like that.
You'll agree with that one, huh?
I'll go along with that.
Now, today we have several updates that we want to
Right.
get to. There's a lot of things happening. In fact, right now in real time, the astronauts that were on board the space station for several months have now returned.
Have now returned.
So they're no longer stranded.
Were they really before? I mean, everything I was saying said they were like, no, we're supposed to be here, you know?
Well, it depends on the person you talk to.
Oh, okay.
That is, it depends on the government official that you talk to. I won't go any further than that.
Yeah, probably for the best.
So they have returned anyway. So
They've returned.
That story has come to a closure. It'll be interesting to see if the Boeing Starliner goes up again or if it actually gets scrapped. You know, Boeing took a big hit recently
They did.
in terms of their financial well-being.
Yeah.
So I don't know what's going to happen. I heard rumors they were going to jettison all of their space rocketry involvement.
Okay.
Maybe they're thinking about sticking to fixing their planes and worrying about that kind of part of their manufacturing.
That's kind of unfortunate because that means the big three private space organizations, Boeing, Blue Horizon, and SpaceX, are down to two, Blue Horizon and SpaceX.
And Boeing's been involved in the space program for a long time. I remember in the 60s seeing pictures back in the 60s.
Right.
Of scientists putting the astronauts in the capsules and stuff, and you see like Boeing prominently written on the back of their outfits that they were wearing. So I know they've been involved in the space program probably since day one.
Right.
And it's a shame, to have them involved to the point where it's no longer viable financially to be involved.
Right. Well, space is expensive. I mean, that's the bottom line.
Yeah, not to go off too far on a tangent, obviously, is issues related to the Boeing aircraft themselves, because it's all one company. So if it hurts you on one end, it's going to hurt the other end as well.
Right. So focus on one, get it working right. Then maybe worry about some other things.
Yeah, we'll see.
We'll see.
So we want to start up our news item for today. So today is an update on Sphere X. We've talked about that several times in the past.
Mm-hmm.
And so finally it was launched last Tuesday, March the 11th.
Okay.
So it's on their way. Everything seemed to be successful. Now remember, the beauty of this space telescope is that it's an infrared telescope. It's not the largest infrared telescope that's ever been launched. You could argue, and what's arguably the largest, and no argument, is the James Webb Space Telescope.
Yeah.
It's about 6.5 meters in diameter, roughly, equivalent aperture size. And you can see the numbers here. This is 0.2 meters in comparison, so really tiny, only 20 centimeters in diameter. The beauty of this telescope, though, is that it can sample over very narrow wavelength range
Right.
of the distribution of the light that's emitted from various objects, like galaxies, for example. So it's like you had a very narrow band filter in front of the camera itself. And as you see there on the right side, the writing, it's about 102 of these filters that it can use.
Right.
So we'll get very fine sampling of what in astronomy we call the spectral energy distribution of an object. It's just a fancy term that really means how bright is this object at a certain well-defined range of wavelengths, and how bright is it at another range of wavelengths, and then another one, and another one, and another one. And if you do that over enough coverage in total of the spectrum of the object, that can tell you a lot about the actual source itself in terms of its makeup, if you think of a galaxy, its composition in terms of the different stellar populations that attribute to the light that you're gathering. Here, of course, in the infrared, and so on and so forth. So there's a lot of detailed information we get from the analysis.
It can tell you a lot of information about grain size, how much dust is there compared to gas, and just, a lot of stuff about the composition as far as the physical characteristics.
That's all tied in directly to star formation. And that's one of the things we like to know, of course, is the nitty-gritty details of where do stars come from.
Right.
And you know they're formed. You look around, you can see them, right? You look up the sky at night, you see stars if it's clear. So obviously nature found a way to make them. But what are those details?
What are the details?
What are the different ways you can form stars, for example? And stars are not all identical. There are different types of stars. Why are there different types of stars? What determines a certain type that gets formed in a certain stellar nursery?
Right.
These are kind of the questions that we like to figure out the answers to, and this is a tool that will help in that perspective.
Excellent. I think it's a great thing.
Yeah, so we'll look for great science to come from this telescope. So far, so good.
So far. It launched.
Yeah, and didn't blow up.
And
didn't
didn't
end
blow
up in a, bottom of the ocean somewhere
Right.
and all that hard work gone down the tube. So everybody's excited who's on the project, of course, for that to happen.
Yep.
So hopefully the telescope will obey and work properly, at least till we get sort of the nominal science out of it.
That's it. So.
Now, the other update, and there's been a couple landers that have gone to the moon recently. So this is one of them. This is the second attempt. I don't know if you remember the first attempt is from the intuitive machines. You remember this first spacecraft kind of did lateral translation along the surface of the moon.
That's
hit
the
a
one
rock
that
and
it's
tipped over
because its legs broke and
Yeah, its feet were in the way, right?
Yeah.
So if you're moving sideways along the surface of the moon and you come to a boulder or something, and you hit that boulder, away
over
you
you
go.
go.
So that's what happened to the first machine.
So didn't it kind of happen the same way this
Well,
time?
this one, I don't think they know. I mean, I don't know if they know exactly, but what they found was, and you can see here's a picture taken from the lander itself on the moon. You can see two legs are up in the air, so it's like it's resting on his back, if you want to think of it that way,
Right.
inside of a crater. So it landed in an uneven place
And tipped
and
over.
tipped over. And this is a beautiful shot. You can see like the earth between its legs, which is kind of weird looking. But it's very interesting, and it's that from this perspective, you can almost see exactly what happened, which is, I was going to say it's kind of cool. Of course, the people who worked on the lander spent all
Don't
their
think it's
time-
cool.
Don't think it's cool at all. But we know some of the instruments worked. Obviously, the camera still functioned when it was laying on its side. The problem is it has solar panels on it, and it has battery that can be recharged from that solar panels. But the solar panels need to be in the sunlight, and these solar panels are not in the sunlight.
Are not in the sunlight.
So the lander only operated until the batteries drained, and that was the end of it. So the mission is kaput.
Kaput.
It is done. But we still get a couple beautiful pictures from it.
Absolutely.
That's something. So, yeah. Now, some people argue if you actually look at this lander upright, it seems to be a lot of structure above the legs themselves. And people
Right.
wondered, is the center of mass too high up?
Right.
So it's prone to tipping, especially on an uneven surface like the moon itself. Now, the intuitive machines say, no, this is not the case. Actually, the center of mass is much lower than what you think just by looking at the overall shape of the structure itself.
Okay.
It's much, much further down towards the surface of the moon where it would land.
So they got something going on that are like the concrete blocks in the bottom of your washing machine.
Right, so there must be a lot of mass then that's down further
Yeah.
in the base of the spacecraft, closer to where those leg structures kind of emanate from to allow it to be less prone to tipping. But you can imagine this is twice now. So if you're an engineer, I mean, one of the things I'd be thinking of, is there a way that we can build some kind of, maybe you don't want to be on legs, 4 independent legs like you see here. Maybe you can be on like a giant, I don't know, like, you go to sleigh coasting and you get on these metal.
Pylons.
Well,
or
no,
something.
it's like a bowl that you're in. This very
Oh, okay.
shallow metal. I don't know what you call them, a dish or something, right? If you had that on the bottom, it's like Weebles Wobble, but they don't fall down, right? If you can design it that way somehow that it can right itself,
right?
If it ever landed in a peculiar way, that would save the mission.
And we've got experience with that because the Sojourner mission to Mars with the balloon bouncy thing had that type of system in it.
Yeah, for sure. So you can sense what is the upward direction,
right?
And kind of have an inflationary type device, which is what you were talking about on Mars. So you can inflate it in such a way that it can right itself.
Right.
And in fact, if the Apollo capsule that landed in the water on return from the moon, it could have easily have landed so the cone part, the top of the capsule, is pointed down in the ocean.
Which would have been bad.
But they had flotation devices that inflated that would right the ship, so it was pointing upwards eventually. So that was all built in. Of course, it's easier to do it in water than it would be on the surface of the moon or on Mars. Right. But I'm sure they could engineer something that's a little better than what's happening here.
What's happening, yeah.
Look, I mean, ultimately you want to go to the moon and you want to go to very interesting places, like the South Pole or the North Pole or some really rugged terrain, because there's a lot of
geology that goes on in the rough stuff.
A lot of very interesting geology that you can see. So why not go into those, the different valley-like structures that you see and so on. And because if it's a really hazardous environment, probably most of the time you're going to be tipping over in this type of design.
Right.
So maybe they'll look at something different. I don't know. We'll see. But we do have, of course, the Lunar Reconnaissance Orbiter that's an orbit around the moon. And if anything lands on the moon, one of the things NASA likes to do is take an image of it. And not only does it allow you to see what state the lander is in, good or bad, but it also gives you a very precise location of where you are on the moon itself.
Right.
No guessing involved. And that's exactly what we see in this image here. So the image on the left is kind of a zoomed out view, and it's an arrow pointing to where the lander is located on the surface of the moon. If you look carefully, it looks like it's in a little small crater. In fact, if you look on the panel on the right, first you have that yellow arrow pointing to the location of the lander, but then you have that little insert that shows you a zoomed in version of it, and the lander clearly landed inside of a small crater, and that's why it tipped over.
Right.
So it could have went, on either side, and then, there's a huge crater, look just north of where it landed.
Right.
So, but anyways, what do you do, right?
What do you do? I mean, to me, that would have been one of the things, put some kind of sonar radar system on it that it is figuring out, hey, the surface I'm trying to land on is this way, move to the side a little bit and see if we've got a better surface,
Yeah, and so that craft was trying to land at the South Pole, at least as far as you can get to it. And by its very nature, it's very rugged. In fact, if you have a telescope, even a small telescope will do, wait until a night where you can see the moon, not necessarily a full moon stage, but some other stage prior or after that. And if you look near the South Pole of the moon, you can see how rugged it is very easily in a small telescope. It is heavily, heavily cratered.
And I'm going to chime in with, why don't you want to look at the full moon? One, it's too bright. Two, because of the brightness, it's low contrast and you really can't see the details.
Yeah, when you're looking at the full moon, the sun is kind of directly above the surface you're looking at. And so the craters, the walls of the craters cast no shadows, essentially.
Right.
And it's really the relief that you see when you have the long shadows, like the sun is much lower in the sky if you were standing on that moon's surface.
Right.
So the full moon is actually a bad time to see the details of the surface of the moon in terms of getting that height perspective, that three-dimensional perspective that we see with our eyes. So it's near the surface. I mean, obviously, the Lunar Reconnaissance Orbiter took a picture of it, so you know exactly where it is. I didn't see any positions that were actually published. I
haven't seen any lat longs or anything like that.
So I was interested to see how close it got to the South Pole. So what is the south latitude on the moon? I wasn't able to come up with a number, so that would be interesting if I do find that. But of course, NASA knows where it is because they've located it.
Right.
So we know the reason why it tipped over anyways. It's just very unlucky in that perspective.
It dropped, and it looks like it's on the rim of a crater. If it had been in the bottom of the crater, it might still would have had problems because it had been in the bottom of a crater. in the shade, but
Well, it could easily land it on the rim of the crater, on the inside of the crater, and that surface is heavily tilted. That
Right.
is a large slope, large
Yep.
negative slope. So it just fell over,
over.
at that point and then came to rest near the bottom part of the crater.
Mm-hmm.
So it's unfortunate, but hey, as they say, those things do happen. But
then there's this one.
there is the second lander, which was Firefly Aerospace Blue Ghost lander, which was highly successful. It landed on the moon back on March the 2nd. I don't know why it was launched at roughly the same time as the Intuitive Machine lander. I don't know if that's coincidental.
I don't think it's coincidental. I think they were both trying to get there where they'd have 2 weeks in the sun.
Yeah, but you can always time that every month, right?
Fair.
I mean, why wasn't
I
it
don't
launched
know.
3 months from now, one of them? So I think
Yeah.
it was more coincidence than not.
Okay.
But they happened to be launched at relatively at the same time. So anyway, so this spacecraft landed. This wasn't going to the South Pole. In fact, it was closer to the equator of the moon itself.
Right.
The image you see here and the yellow arrow is pointing to the exact location of the lander. So once again, the Lunar Reconnaissance Orbiter from NASA took an image of it so we know exactly where it is. They did publish the coordinates, so that's why I was able to write it down. So for those of you who are really keen on this stuff, so you can see it landed at 18.5623 degrees north. So that's really, 18.5 degrees from the equator.
Right.
So it was an equatorial or close to, equatorial type of landing spot on the near side of the moon. It wasn't trying to go to the far side or to one of the poles or the others or anything exotic like that.
On Earth, this would still be well within the tropics. So,
Now, the interesting thing about the Blue Ghost mission is that it was on the moon functioning at the same time that we've had a lunar eclipse last week.
oh yeah.
So we had mentioned this in a previous podcast that the lunar eclipse, at least for those who are in the Western Hemisphere, was going to take place on March the 14th. Lucky enough, it was cloudy prior to the total lunar eclipse, and then it cleared off magically
right.
during the total lunar eclipse till almost the whole thing was over, which was roughly 1:30 in the morning to about 2:30 in the morning our time. And so we got a good view of it. Wasn't like completely clear, but it was close at times.
You got a good view of it.
I did.
From my location, just a mile or 3 away, I didn't. I was clouded out.
Oh, wow.
So-
Yeah, I had a beautiful, and it was so localized because of the clouds coming in and out of the view. And there was one patch where it was relatively clear.
Right.
It was like high cirrus around, but it was no really thick clouds that completely blocked the light of the moon. So I was able to see it. And of course, I could use my binoculars and to
Excellent.
keep an eye on it, which was really cool. And that's what you see here is an image of the moon taken during the lunar eclipse. That's on the far left. But what you see on to the right of that image from the moon is actually what it looked like during this time from the surface of the moon with the Blue Ghost lander.
Nice.
And what you're seeing is, first of all, you think of what causes a lunar eclipse. That's when the moon enters the shadow of the Earth. So at that point, the sun and the Earth and the moon make a straight line, essentially. Mm-hmm. So if you're standing on the moon looking back towards the Earth would be blocking the sun. So you would see a solar eclipse. And that's what you see in this image. So from the location of the lander, notice that the sun is almost completely covered in this view.
Yeah.
So there is the Earth then, which is the black disk silhouetted on the bright surface of the sun itself. And notice the ring going around the Earth. You
I was
see
about
that
to say,
ring?
that's the atmosphere, isn't it?
Exactly right. That's the atmosphere of our Earth. So if the Earth did not have an atmosphere, number one, you got 5 minutes.
Right.
However long you can hold your breath. But the other thing is, this is the light being bent and refracted through the atmosphere of the Earth coming from the sun.
Which is why it's blue in most locations.
Yeah,
And-
which is why you see it, the light going around like a ring of fire around the Earth. Now, interestingly, this is not the first time an image like this has been taken from the surface of the moon. If we go back to 1967, in particular April the 24th, there was also a lunar eclipse, and the Surveyor 3 spacecraft was functioning on the surface of the moon and took an image of the Earth during this time period. And that's the images that you see on the far right.
So about what you'd expect for the low resolution video that we had back in 1967.
Yeah, so it's amazing. I mean, a lot
But
of
it
times
still looks much the same.
Yeah, and you get caught up in this hype of thinking, oh, intuitive machines or blue ghost just landed on the moon. This is the first time we've done this since the 60s, right? So this is something we've mastered decades and decades and decades ago, but they always throw in, oh, this is the first time a private company has done this.
Right.
And in some sense, it's an exaggeration because a lot of the scientists and engineers that work on space probes are not totally employed by NASA directly. They work for aerospace companies that are contracted to NASA to build things.
As we said earlier.
As you said about Boeing. So Boeing and Rockwell and all these companies in the past, right, that have done work. General Dynamics was a famous companies that did work for the space program. The Grumman to build the lunar module for the Apollo program.
What is it? Begins with an R.
Rockwell?
Not Rockwell. They do a lot of missile work still.
Raytheon?
Raytheon.
So all these kind of companies are private companies. They're just contracted out, building things for the government. So in that sense, I always think it's a little bit weird. You're kind of blurring the lines here.
Right.
It is a good achievement. A company without getting government money goes ahead and builds something that land. In fact, you could have very smart university students could do this.
Yes.
All they need is the money.
All they need is the money.
So they can pay for the launch vehicle, right? And they could build the actual lander in-house in their university, in the engineering department, whatever, and then give it to NASA to launch for them.
Right. Or SpaceX or Boeing or anyone else.
But anyway, so it was kind of neat to look at the comparison. And by the way, the Blue Ghost mission finally ended just the other day on March the 16th. And the sun went below the horizon, and it operates on solar panels. So the battery only lasts so long without being recharged, and that's the end. It would be another 2 weeks before the sun peaks up over the other horizon.
And it can't run a heater for that long.
No, so it's essentially done. I don't know if they're even going to try to communicate with it, but they know their instrument. If they think that a really cold weather, minus probably 200 some Fahrenheit at night, is going to be enough to cause electronic components to fail on the lander, then they won't even try.
I gotta admit, I'd have to send a signal.
Yeah, I would too. I would see if there was anything there.
Yeah.
But that's just me. You never know. So why not give it a shot?
Why give it a shot? What does it cost you?
Yeah, what does it cost you? And this actually reminds me of something else. So that I've seen in the news lately. I didn't put up a slide for, but I don't know if you heard this, Robert. That some of the Voyager instruments have been shut off.
Yes, I'd seen that.
You seen that?
Yeah.
So those spacecraft, which are well beyond the orbit of Pluto,
right,
they have heaters on board to keep them at minimum temperature.
Radiothermal batteries are generators.
Right, and so they have to use power, right? Some of that power that's produced by the radioactive decay of the plutonium has to be used for the heaters.
Right.
Because if you let it go to the coldness of outer space, you're in temperatures of like minus 250 or so Fahrenheit. Right. And that will kill the instrument.
I was about to say, and solder cracks and things come disconnected and things like that.
Yeah, a lot of nasty things. I mean, just think of us. Imagine someone dumped you in a minus 250 Fahrenheit environment. Would you cry?
I think I would cease to function.
You'd cry, but you never see any tears because there'd be a solid ice, right?
Right.
So, yeah, you got to keep that minimum stuff running. So Voyager has been launched over 50 years, like in 1977. So these spacecrafts are dwindling in terms of their power output from their generators.
It's reaching close to the half-life of the plutonium.
Yeah,
wasn't
and it's reaching close to the minimum amount of power they need to function.
Right.
And the way to kind of extend its life is kind of shut off everything you possibly can.
Except for the high gain antenna.
Yeah, they'll be able to communicate with Earth, and then minimum like a heater running or something like that.
Right.
And eventually everything else is going to be shut off. Yeah. So it's getting to that point, unfortunately.
It is. But those missions have done so much, though. It's like you're eking out those last little dregs at this point.
Yeah, so you could ask the question, what are you even doing way beyond Pluto?
Right.
And what they're doing is measuring the charged particle fields, the influx of charged particles from the environment of stars in our galaxy, cosmic rays and all these kind of things, which we've never measured that far out before, so it's all new information. But they're not taking photographs. And if I remember right, they don't even have the power to turn the cameras back on, even if they could operate.
Right.
It would just take too much electricity. You just can't afford that. So at this point, and you could always argue, well, couldn't you put more plutonium on board? So instead of running out after 50 to 60 years, it would last 100 or 200 years. But then is it worth the extra cost of having even larger rocket to send it on its trajectory the way we did? And you're only measuring charged particle in magnetic field environments out there. I mean, there's a cost
benefit analysis
that gets done on all these type of spacecraft.
Yep.
In fact, where they had Voyager 1 and 2, there were supposed to be 4 of them.
Right. And they were shut down.
Yeah, and I think it was the Nixon administration nixed it. Ha ha ha. And so now it was only Voyager 1 and 2 at the end. But lucky they got that, because I think some government official says, do we really need 2? Why don't we send 1?
Right.
And NASA would have to argue, say, well, wait a minute, we can't send both a spacecraft, right, onto like Jupiter, Saturn, and then Uranus and Neptune.
Right.
If we want to get close to Titan at the time, then that's the furthest you're going to go in terms of close encounter with other planets, is Jupiter and Saturn. And then the path is such that there's no way you can reach Uranus, Neptune, or Pluto. So there were trade-offs made, and they decided, okay, one will go close to Titan, but that's the last visit to any planet in the solar system. The second one will continue on to Uranus and Neptune and not fly close to Titan. Mm-hmm. Now, hindsight's always 20/20, right? We discovered that even if you're really close to Titan, Titan is completely cloud covered, and the only way to see down in it is looking at wavelengths other than optical light.
Yep.
And you didn't really have the cameras on board the Voyager spacecraft to do that type of observation. Later on, follow-up Cassini mission that went into orbit around Saturn was able to do that. So if we would have put both spacecraft towards Titan as close as possible, we would have wasted both of them. We never would have gone on to Uranus and Neptune. Right. And so that would have been a shame, but we didn't do that, thankfully.
Now we found out that we really kind of want to go back to one or both of those planets, Uranus and Neptune, one if not both of them, because they're different from Jupiter and Saturn.
Yeah, it's a logical step, right? You send out a spacecraft, let's say, to the moon for the very first time. You fly by the moon rapidly and go into orbit around the sun. That's kind of the easiest thing to do technologically speaking. And then you develop the technology to actually, have a rocket booster to slow the spacecraft down and go in orbit around the moon, then make detailed observation. That's kind of the next step.
Right.
And then a lander, if you're talking about an object that you can actually physically land on, like the moon we can, of course. And these are just follow up, pushing the technology, doing different and improved our scientific objectives here. But so Uranus and Neptune would be a flyby mission. The next mission will be orbital type missions.
Right.
And then future generation will be missions you're actually landing spacecraft on the surface of the moons around these planets.
Right.
The planets themselves are completely gas. So you'd have an entry probe like we did, right? Mm-hmm. We've done that for Jupiter, for example. So I could see doing that for Uranus and Neptune. You have a probe that continues to send back data to the orbiter above until the pressures get to a point where it destroys that entry probe.
Right.
So we could do that for sure. And also landing on the surface of the moons.
Right. Like Miranda. And,
all of those. Ariel.
All of them. Ariel.
There's all kinds of new worlds to be discovered.
Absolutely.
And it's not going to be done in our lifetime, Robert. I guarantee you that.
Speak for yourself. I plan on being around, dang it.
I can only say one thing. You better start on that whole food, plant-based diet if you plan to live long enough to see that kind of stuff happen.
I keep saying they're going to pull my brain out and put it into a machine body, and I'll be happy.
I thought you were going to say in a jar of pickle juice.
That would work too.
Wait, future doctors to figure out how to meld that in with some the Borg. Then you'll be Swedish, as they say, right?
Then we'll be Swedish. All right.
Okay, so this is an interesting report that was done based on some information that we had reported, I think it was back in January.
Right.
Now, this is related to the idea that right now, astronomers have this disease, as we always say, called aperture fever. And this disease really means that, if you get a telescope for Christmas, this is how I kind of like to describe it to my class or anyone else I talk to. You get some size telescope for Christmas as a young child, and then you use that telescope for a whole calendar year, and then the next Christmas is like, Mom and Dad, could you help me write this letter to Santa? I want to get a telescope. And they're like, Well, Johnny, you already have a telescope. What's wrong with that? But Mom and Dad, I've used the telescope fully. I can no longer do anything new with it. I'd like to have a larger telescope
so that I can see more details.
I can see fainter objects. Yeah, more stuff. So you're always trying to get a larger and larger and larger telescope because it allows you to see fainter and also provides a higher resolution.
More details.
So that's aperture fever. So astronomers right now, optical astronomers, for example, are trying to build these very large telescopes. The largest optical telescopes right now that we use are on the order of about 10 meters across. So that's about 30 feet across. So these are huge telescopes. They're not small. But of course, we want to go bigger than that. Go big or go home. Isn't that the saying, Robert?
I guess. But I don't like that saying because I will state up front. People underestimate my desire to go home.
Home is where the heart is, Robert.
That's right.
Now, what do we mean by large telescopes today? Well, we're talking 30-meter class telescopes.
Right. So about 100 feet across.
So these are huge, and there are different competitions. We have the Giant Magellan telescope, that's close to 30 meters equivalent, being built down in Chile. We have the 30-meter telescope, the TMT, which is trying to be built on top of Mauna Kea in Hawaii. And if this has been shut down lately because of, court cases involving the local residents' desire of not putting more telescopes on top of Mauna Kea. In fact, some people want them all down, no telescopes on top of Mauna Kea. Why go there? Because it's one of the best sites in the world to make observations of the sky. Number one, it's clear often. Number two, there's less turbulence above the telescope. So what we say in astronomy, the seeing is better. So there's a push to do that. Okay. Yeah. Now, the Europeans are trying to build a large telescope as well. And remember the story that they were going to build something about 150 meters across called the OWL telescope.
Okay, I hadn't heard about that.
Yeah, and it stood for the overwhelmingly large telescope.
Yeah, that would be it.
To go from about 8-meter size, and if you include the telescope that's in the Canary Islands at La Palma, about 10.4 meters in size, then that's a big jump to 150 meters in size.
Right. So
the governments in Europe said maybe you should make a smaller telescope. Okay, so we won't build a 150-meter telescope, but we got to beat the Americans. So instead of a 30-meter telescope, they're building a 39-meter telescope. Okay. So that's what the money's been allocated for. Well, they're building it in Chile, near where they've got lots of other larger telescopes. And what the story here is about is there is a sort of a facility, a plant, remember that was based on the hydrogen, right? Hydrogen capture and is related to green technology and stuff that's being built just a few miles away. That would
who thought that was a good idea?
That would completely disturb the operation of this much larger telescope when it's finally done, I think in 2027 or late 2026.
I'm going to sit here and say they've spent all this money to build this thing, and if they build this INNA facility, it completely destroys the usefulness of the telescope. So
now, speaking about telescopes,
right?
Well, when I go to buy a telescope, as I did as a young child, I kind of take all the money I can and try to buy the biggest one possible.
Right.
And some of these really high quality telescopes can set you back a lot of money.
Right.
You're talking, $5, $6, $7, $10, $12,000. I can't afford that.
Right.
And I'm not going to spend that much money at this point in my life on a telescope that I probably wouldn't use that much. So it all really depends on the amount of money. Now, what you can do is you can buy a really cheap telescope for $50, and those are essentially useless. Right. The optics are really bad. The stability on the mount is so poor, it's hard to see in, and everything's shaking inside, and you can't, settle in, let's say on Jupiter, to see the moons of Jupiter nicely. Mm-hmm. I paid for a 12-inch telescope. I paid like $600 for a Dobsonian. So Dobsonian is these more larger aperture-sized telescope. They just don't have the setup that you can hook a camera to it and do long exposure photography. Right. But for just viewing with your eyes, they are fantastic. You get a lot of aperture size for a relatively small amount of money.
And unfortunately, one of the big companies that made those, Orion, has gone out of business. So the only two big companies still making consumer level telescopes, honestly, are Meade and Celestron.
Yeah, so you have to just shop around. And the
You
other
have to
thing
shop
you can,
around.
sometimes you can pick up some telescopes like somebody, it's like exercise equipment,
Right.
right? You go out and you get exercise equipment for January 1st, and by the time you get to March, you're done with it. And you got this $1,000 treadmill sitting in your house somewhere and never use it. Why not sell it to someone who could use it?
Right.
So sometimes you'll see telescopes for a reasonable price for sale, and you just have to be careful to check the optics, make sure there's no scratches or pits or anything like that.
Right.
So,
So in that case, get them to take you a picture of the primary mirror shine their light down the barrel of the telescope, so to speak, and take a picture of it.
and the best, of course, is if you could actually go see it
Go see it.
physically and even get someone to show you at night, like look at the moon with it to make sure that everything is working properly. So there are different ways you can think of. Just stay away from those cheap, as we used to say, department store type of
Right.
telescopes that are kind of useless.
The only people that you should be getting one of those telescopes for is your 6-year-old, in my case, grandson. I'm probably going to get him one of those simply because he's not where he needs to see anymore.
And the other thing you can look at is a good pair of binoculars at that
Right.
age.
There you go.
Because then you could sit on your back on a lawn chair, like a spread out lounge type chair,
Yep.
and have them resting against your eyes or something, and they'd hold them nice and steady.
So
Yeah.
in the end, Meade, Celestron, try to find somebody who's selling an Orion Dobsonian are your best bets.
Now, getting back to the construction of this plant near the site of these large telescopes, including the 39 meter that's being actively built. And don't forget, this 39 meters like €1 billion.
Right.
They're not cheap. So we're talking about a lot of money invested into this area of Chile. And Chile has an agreement with the countries around the world that they get to use like 15% of the time on every telescope you put on their territory.
Mm-hmm.
And Chile is one of these areas where you have really good viewing.
Really good
of the
viewing.
sky,
It's
good-
high altitude and
up in the Andes
dry.
Mountains. It's dry and good seeing and clear often. And the other thing is you get a good view of the southern sky.
Right.
And it turns out that the center of our galaxy is right overhead if you live in the southern hemisphere.
Yep.
And if you live around where we are in the northern hemisphere,
It's
North
low.
Dakota, it's
Low.
right on the southern horizon, essentially,
Yep.
the center of our Milky Way.
Especially since it's towards Sagittarius, which is a summer constellation,
Yeah.
and it's even lower on the horizon.
Yeah, so if you want to see where the center of the Milky Way is, go out at night in July, if you're in our location, and look towards the direct south. That's towards the center of the Milky Way galaxy.
Yep.
But
Look
if you're
towards the teapot.
but if you're down south, the southern hemisphere, which I've gone there several times, the center of the Milky Way is right above at times. And it's
Okay.
amazing. It's a fantastic view.
I gotta get
and
down
just
there.
to share a little bit of experience here, I remember I went down to Chile for the very first time in April. And it was at that time in the middle of the night that the center of the Milky Way was directly overhead. Not only could you see the large and small Magellanic Clouds with just your eye,
Right.
when you looked at the center of the Milky Way in a dark location where I was, it was unreal, the experience. That's all I can say. There is a dust lane that cuts through the center of the Milky Way.
Mm-hmm.
And to me, it almost gave me appearance of a 3D effect, like it was sticking out in the foreground from
Which
the Milky
is.
Way. Yeah, but you actually can sense that with your eyes. It's
Cool.
amazing. I've never seen that before from the northern hemisphere because the Milky Way is always down in the blurring and mucky part of the atmosphere near the horizon. So it's if you ever get a chance to go south, south of the
I want to
equator,
take it. Yeah.
try to get
Yes.
get an opportunity to see the Milky Way. It's just unreal.
Yeah.
It is really awe-inspiring, as they say.
mean, I grew up in the southern part of the U.S., so I got to admit, during the winter, the Milky Way was up overhead, and I got to see some of that growing up. But, since then, there's a lot more lights and things like that wash it out.
Well, you can easily tell why different cultures that are from the southern hemisphere
Yeah.
have that prominent in their society about the night sky.
Right.
Because with normal vision, it's just unreal what you actually see. So it really captures your imagination.
Yep.
So anyways, getting back to this planned site for the European Southern Observatory extremely large telescope, 39 meter telescope, they did a report on what impact the manufacturing of this plant nearby would have on observing in this area. You can read, this is the conclusion of the executive summary of this report. So maybe we could just parse through a little bit. As a conclusion, the project, the INNA, that's the plant, would degrade the performance of all the telescopes at this location in Chile to unacceptable levels. So even the ones that have been there for many years now operating, and like I said, Europe has an agreement with Chile where Chile uses 15% of the telescope, and then they put a lot of money in that location. Right. So it's not like we're taking their land from them and somehow using it to their disadvantage. Chile is getting a lot from this.
Right.
And has been for many years.
For many years, yeah.
So, and it says here, the driver is the very short distance from the facility to the observing site. That's why this is negatively affecting things, is it's just so close. As all mitigating actions have already been taken, these negative and unacceptable impacts cannot be avoided or mitigated unless the project moves away.
Right.
Should the project be approved, so it hasn't had the final approval yet, the value of the telescopes installed or planned by the European Southern Observatory would be substantially decreased. These losses are manyfold and are not recoverable worldwide. There's no other good sites in the south like you have in Chile.
Right.
That's the problem. So of all the places, and Chile's a large country, it's stretched north and south, right? Rather than, east-west. You can put this facility somewhere else. And I don't understand the hesitation by the Chilean government of not moving and giving the economic impact of astronomy to their country. I don't understand.
That's what I'm saying.
What's the reason?
Why can this facility, this INNA, not be put somewhere else? It needs to be on a mountain, okay? There's plenty of mountains in Chile. Why not somewhere else?
There's got to be some other place you can put it.
Right.
Rather than impacting astronomy as it is. But we'll see. Like I said, the final approval hasn't been given to this project. So
maybe they'll see sense.
Yeah, hopefully. So we'll keep an eye on this story and let you know if we hear anything.
Yep. So the next one?
So the next one, this is an interesting paper that has recently been announced, the study. And this involves an object that we've actually talked about also not that long ago, you may recall. And this is the discovery of 4 sub-Earth mass planets in orbit around Barnard's star. Now, Barnard's star has an interesting history. It was first sort of came to attention back in 1916, so during the First World War, by E.E. Barnard, okay, hence the name Barnard's star. And the reason why it captured his attention is it has the largest motion across the sky, which we call proper motion, of any star.
Right.
And for those of you who know about proper motions and are interested in this, it's on the order of about 10.3 arc seconds per year. So you can take a series of images taken every year, for example, and you would see the star move relative to more background stars significantly during that time.
Right.
So it's a fastly moving star. Number one, it has a large space velocity, which we say, so it is moving fast, but it's also very close to us.
Right.
So
which is both of them lead to why it has such a large proper motion.
Right. And so you could think of it as like an airplane, right? When you're at the airport watching a plane take off, it covers a large angular distance in the sky because it's relatively close to you. And at the same time, you might look overhead and see a plane at, 39,000 feet that's barely moving across the sky, but it's going a lot faster than the plane that's just taking off from the runway.
Right.
Because it's so much further away, its angular distance that's covering is much less.
Mm-hmm.
So Barnard's star is on the order of about 6 light years away, and then we can measure this with the Gaia mission. I think that's why we talked about it in the past.
Right.
In fact, if you look at the uncertainty in the distance, is amazing. And that's all from the fact that you get very precise measurement with both its parallax, right, and the proper motion impact on that parallax. So you can see there, 5.9629 plus or minus 0.0004 light years. It's amazing, that high degree of uncertainty on that. It's such a small value.
I'll sit here and go, it's now a potential target for an interstellar mission
Well, it is
because it's got 4 planets.
yeah, it's one of the near. It's not the nearest star. The nearest is Proxima Centauri, but it's really close, and it also has planets, as you mentioned, and so does Proxima Centauri. The Alpha Centauri system has planets. So there's 2 targets now that are relatively nearby.
Right.
Now, this star itself is a low mass star, and you get that from the spectral type M45. So it's a main sequence star.
Main sequence,
Which
right.
means it's converting hydrogen to helium in its core, a similar stage that our sun is at.
I got to ask, have we gotten a good age estimate on that Barnard star? Is it
Not that I know of. I mean, that's
Okay.
one of the problems with a star that's isolated,
right?
is how do you get a good age of it? And you really can't.
You really can't.
The reason why we know the age of our sun is because we radionuclei date the rocks in the Earth, and we assume that the Earth and everything else in the solar system, including our sun, formed at approximately the same time. So that's why we know our sun is about 4.5 billion years old. But if you have an isolated star in space, it's very difficult to precisely measure its age. So that's a problem.
I was just wondering if there was some evolutionary feature about it that they'd know. But then again, M dwarfs live for
The lowest mass ones could go up to a trillion
years. So yeah,
before it runs out of hydrogen in its core, because such low mass it doesn't need to have a high rate of burning through its fuel to provide the internal pressure support to prevent it from collapsing in on itself.
right.
So they last a long, long time.
And you add in that we're doing a lot of stellar evolutionary theory here, folks, but they also are convective throughout their whole,
That's
interior.
right. Exactly.
So they can keep churning the hydrogen, dredging it back down into the core.
Exactly right. Yeah. So this particular planet, these planets, then you can see the masses there on the bottom in terms of Earth mass. They're on the order of somewhere around 0.2 to 0.3 or so Earth masses. So clearly, just
They're tiny.
20 to 30% of the mass of the Earth. So they're not Earth size; they're much smaller than that.
Yeah, the largest is moon sized.
Yeah, the largest there is the 0.335
Right.
Earth
That's
masses.
about the
So
moon,
it's about,
isn't it?
about the moon size.
Yeah.
And orbital periods are about the same, just a few days. And a lot of that has to do with the techniques that you use to discover these things.
Right.
The closer in the planet is to the host star, the easier it is to see the radial velocity, the tug on that star, the Doppler shift that you would measure. And also, of course, if the planet was really massive, it's easier to see.
Right.
So the whole technique is biased that it's more sensitive to detecting really massive planets really close to the host star.
Yep.
In this case, we have, because of the very advanced instruments that we can use, that can detect motion on the order of 30 centimeters per second radial motion. I remember when that was like tens of meters per second. Not that long ago.
Not that long ago. That was been about the time that I was in grad school at Georgia State.
So now you can detect not just really massive planets near the host star, but things that are just 20 to 30% the mass of the Earth that's close to the host star.
Right.
So the techniques the instruments are evolving clearly to be more sensitive for this type of work. So we have 4 planets that we can look at in terms of new discoveries. So let's send a probe.
Let's send a probe.
Let's get working on propulsion to make it a little faster, so I don't have to wait for 500 years or more.
Well, I'm sitting here calculating, with a good solar cell to boost it when it gets outside of thruster range and things like that. We're probably talking, 100, 150 years we could get there.
There, now we're back to our whole food, plant-based diet. Right?
Yeah. Let's talk about 4 more planets.
Yeah, what a coincidence. So this is another recent study, this time with the James Webb Space Telescope, looking at, you can see 4 planets that are orbiting the star HR 8799.
Yep.
So the
HR is a catalog, by the way.
Yeah.
I don't know what the
Henry
letters-
Russell.
Henry Russell, okay.
So, and then it's also known as V342 Pegasi. So it's a constellation of
Pegasus.
And it's one of these weird stars, the Lambda Booty stars. Do you remember what those are?
I don't know what Lambda Buddhists are.
They have a very low abundance from their spectrum, right? Looking at their spectrum of these iron peak elements. So elements near
Near iron.
iron, at very low, unusually low.
Okay.
And so people don't quite know where that's coming from. I don't know if it's material being dredged up from underneath that's swamping the signal, and diluting it or something. But there's something going on with these type of stars. So this is one of those type of stars. The star is actually subtracted from the image so that it doesn't, disturb the light coming from the 4 planets that you see around it.
Because its glare would be out to cover all 4 of those.
For sure. And that's denoted by that star-like symbol and, of course, the label on it, HR 8799. But you can see the 4 planets. We have B, C, D, and E. And the masses of these planets are now in terms of Jupiter's masses that you see in the bottom left. So we have masses that range from about 5.7 Jupiter mass all the way up to about 9.1 Jupiter masses.
Mm-hmm.
So they're much more massive than the planets that we've seen around Barnard star.
It's just not unexpected.
It's not unexpected. And the thing to note here then is JWST has recently captured a spectrum of planet E. That's why there was a yellow arrow pointed to it. And this is the presence you can see in the spectrum of carbon dioxide.
Yeah, okay. I'm going, you've got 3 data points on that.
We're going to get better data.
We're going to get better.
But it's very intriguing, as you can tell
intriguing.
there. So it looks like then that there is carbon dioxide in the atmosphere of this planet.
And potentially some CO, some carbon monoxide.
So it's very, very, very cool when you think about it. So we're getting to the point now where we can actually taste, quote unquote, the composition of some of these atmospheres of these giant planets. Mm-hmm. And that's only going to get better with more precise instrumentation that we send up into space, really good measurements of these objects like that. So that's a whole new science, right? What are the composition of the atmospheres around these giant planets? What's that all about?
Right.
And you could start looking at it. Say, if you have the tools, of course, you can look at thousands of these planets and analyze in relatively great detail what their compositions are all about. And this whole science of exoplanet atmospheres will develop. And that's kind of where we're at, the sort of the early days of this whole new window on the universe in some sense. And then, of course, you do the direct comparison with our own solar system, looking at giant planets and see how they are similar, see how they are different. And why are they similar or different?
Absolutely.
That's the big mystery.
That's the big mystery. That's what we're after because, we want to know why,
Now, the other thing that I want to mention that we've seen lately is new moons discovered for Saturn. So this is a paper that released the first batch of 128 new moons that have been observed orbiting Saturn. This data is taken by the Canada-France-Hawaii telescope. And if you add the 128 to the existing number, this means Saturn now officially has 274 moons recognized by the IAU.
I'm just looking at this and going mind boggled at how many are in retrograde, which means they're captured.
Yeah.
It means they're captured.
Now, this is so many moons, and it's so much greater than the nearest one, which is Jupiter, right? I forget the number there is like 94 or something of that order. And they've already looked around the space around Jupiter and don't see the number like you see around Saturn. So as far as the researchers are concerned, Jupiter will never be able to
catch up,
take the record away from Saturn at this point. But in some sense, Robert, when you think about like the rings around Saturn, those rings are not solid rings.
Right.
They are formed of individual particles. In fact, James Clerk Maxwell wrote a paper on this subject. Mm-hmm. And if you think of those individual particles, some of them are big as a fist, upwards to the size of a large house. So these are like individual icebergs that are in orbit around the planet.
Why aren't they considered moons?
Well, that's it. And if you consider them, then what is the number? Millions and millions and millions of individual objects in orbit around Saturn itself.
So I think there's reason to believe that there's a size cutoff that people are talking about on these. But, yeah.
And the researchers did suggest that there was evidence of an impact relatively recently, within the last few million years, that created a lot of these particles. And that's why you see that retrograde motion.
So, something came in, smacked one of its then existent moons or one of the current moons, blew it all apart.
Yeah, and you can, do simulations of that to see.
Mm-hmm.
And if you knock off enough pieces, they're in their own orbit around Saturn as well.
Right.
Then all of a sudden, obviously you can boost the number of moons that Saturn has.
Yeah.
So if you talk about, as we had done already in this podcast, imagine in the future going and landing on all the different moons of the planets. Saturn alone will keep us busy. We have
For a
274
long time.
worlds to explore.
Yeah.
So we'll have to send out these nanoprobe landers, right? And then we can land on all of them at roughly the same time. Or these CubeSat type of devices, these
CubeSats
miniature
is what I was
landers, right?
thinking.
Really
Yeah.
tiny stuff based on really microelectronics. I mean, really micro nano electronics. We want to always throw in the word nano. It sounds sexier. You see?
Right.
Right? See how that works? And use the word synergy a lot. That also helps. But yeah, so if you can land on all these, maybe you could actually figure out where were these pieces relative to the site of the impact, given their properties, their shapes, what kind of
their compositions,
what kind of structure. I could see like the melting of the water because they're probably made mostly of water ice, and then they refreeze again really rapidly, and you'd see like features on the surface, like different rings, emanating from some site where they froze up, and you could see all of that. So I'm sure you could almost like the cosmic jigsaw puzzle of trying to piece together, the main bodies that collided or something. I'm sure somebody will try doing that in the future.
Oh, I'm sure somebody will take at least nothing else, the orbital dynamics, and try to trace back.
Yeah, and then you can be able to tell, that'd be kind of cool. So these are really, really tiny objects. Luckily, they're made mainly of ice because that has a high reflectivity.
So you can see them.
So you can see them better. Imagine if they're small and made of coal. I mean, so...
I don't think we'd see them then.
No, it's much, much more difficult. You have to wait for a much larger telescope to get to that point. But anyways. And finally, the last thing I want to mention, I don't have a slide for it, is in the news in the last couple days, there has been this report of the fact that our universe may be inside of a black hole. Have you heard about this, Robert?
That again?
This is nothing new. This has been brought up, many, many decades ago.
Times.
And it kind of comes back. It's like I was going to make a joke about a certain disease, but it keeps coming once in a while, again and again and again. So it's back again. This time it's based on the idea. There is this particular researcher who's been publishing papers for decades now that there is a handedness to the rotation direction of galaxies. So think of spiral galaxies. If you think that the spiral arms trail the rotation, then by just looking at an image, you can tell which direction it's rotating in, clockwise or counterclockwise. And of course, that's all relative to us.
Right.
Right? So you have to be aware of that. That there is a preferred rotation. That is that if you'd expect it's randomized, then if you had a large enough sample, 50% of galaxies would be seem to go clockwise from our point of view, the other 50% counterclockwise.
Which that is what we tend to find, is it not?
Yes, and this researcher has been pushing this idea, and I don't see a lot of support for it. It's not like people have been joining and then publishing papers to this sort of coming to the same conclusion as this particular person, who I won't mention. You can look it up easily yourself. Anyways, he's been arguing that there's this handedness, that there's a preferred direction of rotation. And so the latest thing that's happened is he's taken data from the JADE survey, which is this deep extragalactic survey that the James Webb Space Telescope has been doing. And he's looked, I think there was an order of 220 some odd galaxies, and looking at their shape. So these are at high redshift. So in other words, you're looking at the very early part of our universe and doing the same type of measurements and seeing that about 2/3 of them rotate spin in one direction, 1/3 go the other way. And one way that you could show this would be the case if we lived in a black hole that was rotating in a certain direction. So there's a sort of a torsion type of effect happening, a torque, and that things would have a preferred alignment in terms of the rotation, which could provide evidence that we live inside of a black hole, which would then fix a lot of other problems that we have in cosmology, like the Hubble tension, and probably the dark energy and the dark matter, and you name it. You could throw everything in there. Why apples are red and not black when you pick them off the tree, or I don't know, whatever, right? Why the sky is
whatever
blue.
is, yeah.
Anyways, but unfortunately, the news media, because it was published in the monthly notice of the Royal Astronomical Society recently, the news media jumped on this,
Right.
and this story has been spreading quite a bit. But
And like you say, this isn't new. This has been kicked around for a long time.
so I'm waiting for somebody out there who actually put together a very thought-provoking argument of why this is not the case,
Right.
and that'll be out there soon, I'm sure.
But it's not as sexy, so it won't get the news media
Yeah, that's the
coverage.
story that gets published on page 20 instead of page 1. You know,
Right.
that kind of stuff. But Robert, we've come to the end of our time.
Right.
That hour went so fast it seemed like 30 minutes.
Right.
So we are done for the day. Thank you for watching our podcast. If you're interested in science and want to get more involved, there are lots of ways of doing it, including coming to the University of North Dakota. We have lots of really good programs and classes that you can take both online if you're not nearby or on campus itself if you happen to be able to visit us in person.
And come see us if you do.
Now, our next podcast will be a week from today on March the 25th. We always leave you with a quote. And
Okay.
today we talked a lot about the moon. So I dug back into the history of looking for a quote related to the moon. And this is from Wernher von Braun,
Okay.
a very famous person who worked on the V2 project for Nazi Germany. I guess you could say he was forced to immigrate to the United States after the war and helped develop the rocket program, including the building of the Saturn rockets.
Right.
That Saturn V, of which was used to get us to the moon. And so he gave an interview back on January the 7th, 1972.
Okay.
This is near the end of the Apollo program, just less than a year away from Apollo 17, the last visit to the moon by humans. And here's the quote. "I am convinced that before the year 2000 is over, the first child would have been born on the moon."
We're a little behind.
Never make predictions. That's the
Right.
moral of the story.
Well, make predictions, but make them,
Never bet on them.
never bet on them.
Anyways, thank you for watching. If you really liked it, give us a thumbs up. And if you really, really liked it, please consider subscribing. And we'll see you next time.
We'll see you next time, folks. Have a good night.